A comprehension of natural ground forms such as hills, ridges, slopes, and valleys, including the ability to recognize them on a map, is essential to every military leader. A modern and complete topographical map portrays all these forms, usually by means of conventional signs known as contours. A contour is a line on a map representing an imaginary line on the terrain. It connects points of equal elevation. This section of a contoured map shows the characteristic appearance of contours. The numbers indicate their elevation in feet above mean sea level, the origin of measurement of elevation. The elevation of the point A is 590 feet, that of B 580 feet. The elevation of the point X lying between two contours may be determined by interpolation. Estimate the distance from X to each of the contours between which it lies. It appears to be about 6 feet higher than B and 4 feet lower than A. Therefore, its elevation is approximately 586 feet. Let us examine the contours about this hill. Assume that the base is at mean sea level. An imaginary line connecting all points about the base will be the zero contour. 10 feet higher, another line is drawn connecting all points on the hillside which have an elevation of 10 feet. Notice that the interval between contours is measured vertically and not along the slope of the hill. Next, the 20-foot contour is drawn in, 10 feet higher than the 10-foot contour. Thus, the contours appear successively to the top of the hill. Contours are spaced at uniform vertical intervals. In this case, the vertical interval is 10 feet. The interval may be 5 feet, 20 feet, or even 100 feet on small-scale maps. However, it is always the same on any one map. The height of a contour above mean sea level is always measured in feet and is written on the contour at one or more points for the convenience of the map reader. The study of these contours has been made from the point of view of a ground observer. If we should take to the air, an entirely different picture of the hill and its encircling contours would be obtained. This is the way the contours appear when drawn on a map. Every contour is a continuous closed curve. The curve may not close within the limits of the map, in which case the ends pass off the map and meet somewhere on the outside. The small closed contour with no others within it indicates approximately the top of the hill. It is 50 feet high. Another view from the ground allows an examination of the slopes of the hill. It is evident that the slope on the right is steeper than the one on the left. Looking down from the air, it is apparent that the steepness of the slope is indicated by the horizontal spacing of the contours. On the abrupt slope, the contours are close together. On the more gentle slope, the contours are farther apart. The relative spacing of the contours indicates the nature of the slope. Where they are evenly spaced, a uniform slope is indicated. Here is a section of a contoured map showing typical ground form. The characteristic wavy form of the contours indicating irregularities of the ground is at once apparent. The numbers signify the vertical heights in feet above mean sea level. At A, B, and C, the contours are closed curves. Since these contours are higher than those outside of them, they represent hilltops. At A and B, the tops of rounded hills. At C, the crest of a ridge. Most of the contours do not close within the limits of the map. The 200-foot contour runs off the sheet and closes just outside, as indicated by the broken line. It runs off again at this point and at this point, and closes far beyond the limits of the map. The slope from the point A to the stream junction is uniform, indicated by equally spaced contours. Examine the slope from B to the stream junction. Near B, the slope is steep, becoming more gentle near the stream junction. It is therefore a concave slope. From C to the stream junction, the slope is convex, gentle near the top, and more abrupt at the bottom. Here the contours appear to touch. This indicates a vertical cliff. Of course, these contours do not actually touch, as they are of different elevation. It is only their projections on the map which do so. Note the characteristic V shape of the valley or streamline contours. The V's point upstream. Note the U shape of the hill or ridgeline contours. The U's point downhill. Observe the characteristic appearance of the contours at a stream junction. On a water-worn terrain such as this map represents, adjacent contours resemble each other. This simply means that the change in slope and in the form of the ground are gradual. In determining the location of contours, the topographer is guided by a skeleton of critical points, the elevations of which have been determined. Critical points along a streamline are at points where the stream enters and leaves the area, at the source of tributaries, at points where the tributaries join the stream, and wherever the stream makes a decided change in direction. Along ridge lines, critical points are located where an abrupt change of slope occurs, or where there is a decided change in the direction of the ridge. The theory of logical contouring is based upon the assumption that between two adjacent critical points, the slope is constant. This represents the drainage skeleton of an area upon which the elevations of certain critical points are indicated. 10-foot contours are to be sketched in. By interpolation, determine the elevations of all stream junctions not already shown. Take, for example, the one between 91 and 97. Assuming a uniform slope between 91 and 97, the elevation of this stream junction may be accurately estimated as lying halfway between 91 and 97, or 94 feet. Now between 94 and 120 on a tributary, interpolate 100 and 110. Since contours will cross the tributary at these points, indicate them lightly by V-shaped marks pointing upstream. Likewise, between 97 and 135, interpolate 100, 110, 120, and 130. In a like manner, interpolate the contour crossings along each tributary from its source to its confluence with the main stream. The contours cross the streams at equal intervals at points whose elevations are multiples of 10. Next, on a ridge line between 91 and 130, interpolate 100, 110, and 120. Since these points are where contours round the ridges, indicate them lightly by dashes. Continue this process until such interpolations have been made along each ridge. The elevations of these points should be multiples of 10. Finally, sketch in the contours, joining the corresponding V's and dashes. Cross the ridges in broad curves and the streams in sharp V's, which gradually change to curves toward the source of the stream or tributary. Insofar as interpolated points will allow, each contour should approximately parallel the ones adjacent to it. Changes are gradual, corresponding to gradual changes in the shape of the ground. The completed sketch should have all guide elevations removed and the contours numbered. Every fifth contour should be emphasized by a heavy line. In this case, only the 100-foot contour is in this category. The relative spacing between contours on a map indicates whether the ground slope is steep or gentle. This is apparent at a glance to the map reader. The actual amount of the slope, expressed in percent, may readily be determined. Notice that the contours between the points A and B are uniformly spaced. This means that the slope of the ground between these 2 points is uniform. The elevation at A is 140 feet. At B, it is 185 feet. The difference in elevation is therefore 45 feet. Now apply the scale of the map to the distance from A to B. The horizontal distance between these 2 points is 300 yards, or 900 feet. To obtain the percent slope, divide the difference in elevation, 45, by the horizontal distance, 900, and multiply by 100. 4,500 divided by 900 is 5. The slope is therefore a 5% slope. Since the points A and B are on the road, this portion of the road is said to have a 5% grade. The ratio of the difference in elevation to the horizontal distance, that is 45 over 900, reduces to 1 over 20. This is read 1 on 20. It means that a 1 foot rise occurs in each 20 feet of horizontal distance. This expression of slope is known as the slope ratio or gradient. Thus, a 5% slope is the same as a slope the gradient of which is 1 on 20. Ground sloping upward is a plus slope. Ground sloping downward is a minus slope. Examine the slope of the road from A to C. It is apparent that the contour spacing is irregular. The slope between these 2 points is therefore not uniform. In such cases, the map reader selects points along the route at which changes occur in the contour spacing. These points mark the breaks in the slope. Minor irregularities between such points are disregarded. The slopes thus determined represent average slopes along the route. A most satisfactory way of visualizing the slopes of any line along the ground is by an examination of its profile. On this map, we shall construct and study the profile of the line AB. Select a piece of paper upon which equally spaced horizontal lines are drawn. Place the upper edge of the paper near and parallel to the line AB. Refer to the map and determine the lowest and the highest numbered contour lines cut by the line AB. These are 500 and 580, respectively. Now, number 9 consecutive horizontal lines on the paper, from 500 to 580. The interval between the lines corresponds to the contour interval on the map. In this case, contours appear every 10 feet. The straight lines represent the horizontal planes upon which lie the contours from 500 to 580 inclusive. From each point where the line AB cuts a contour, drop a perpendicular to AB. Extend this perpendicular until it cuts the corresponding horizontal line. The elevation of A is 580 feet. A prime is on the 580 line. The elevation of the point M is 570 feet. M prime is on the 570 line. The elevation of N is 560 feet. N prime is on the 560 line. The elevation of O is 550 feet. O prime is on the 550 line. P and Q are of the same elevation, 540 feet. Therefore, both P prime and Q prime are on the 540 line. This process is continued to the end of the line in question. Each point where the line AB crosses a contour is indicated on the horizontal line corresponding to its elevation. Major irregularities of the ground thus begin to manifest themselves. Minor irregularities of the slope between contours cannot be considered, as they are not indicated on the map. Elevations continue to fall until, after crossing the stream, they begin to rise once more. The point B lies between two contours, 520 and 530. Therefore, its elevation can be estimated at approximately 525 feet. Now connect the points thus established by a curved line. At this point, between two elevations of 540, the line AB descends nearly to the 530 contour. In other words, a depression occurs. Therefore, on the profile, a corresponding depression must be shown. Interpolate a point 7 or 8 feet below the 540 line and continue the profile. At this point, between two elevations of 550, the line AB reaches an elevation of approximately 556 feet. In other words, a crest or hilltop occurs here. A corresponding crest should appear on the profile. By interpolation between 550 and 560, indicate the high point of the crest and continue the profile. Here, another depression or valley occurs as the line AB crosses the stream. It is so indicated on the profile. The result is a fairly accurate picture of the surface of the ground along the line AB. Visibility is a matter of great importance in military operations, entering into problems involving concealment or cover, routes for troops or patrols, sites for observation posts, and possibilities for direct fire. Can a machine gun located at this point be seen from a ground observation post at A? Upon the profile just constructed, locate the machine gun and the observation post. Assuming that the eyes of the observer are about 5 feet from the ground, draw a line representing the line of sight from the observation post to the machine gun position. It is obvious that vision is obstructed by a ridge. The machine gun cannot be seen from the observation post. Now suppose it is desired to determine all points along the line AB which are visible to the observer at A. Draw straight lines from the observer's position tangent to all obstructing crests. It is apparent that the portions of the line AB below these tangents and beyond each intervening crest are invisible to the observer, and that all other portions are visible. This condition may be readily indicated on the map by breaking portions of the line AB. The solid portions of AB are visible to the observer, the broken portions invisible. By the use of the method just described, it is possible to determine the visibility of areas within a sector and from an established observation post. Again, assume that the observation post is at A. Draw the line AC. By the profile method just discussed, determine the portions of the line AC which are visible from the observation post, and those portions which are not visible. Indicate the visible portions by solid lines, and the invisible portions by dotted lines. Follow the same process with the lines AD, AE, and AF. Now outline the visible and invisible areas of the sector by a curved line, connecting the adjacent extremities of the visible and invisible portions of the lines drawn from A. The slope above the line just drawn is visible from A as high as the crest of this ridge, which hides nearly all of the sector which lies behind it. A small portion of high ground near B is visible. This small area is hidden from the observer. It is now apparent that the shaded areas are invisible to the observer at A. The unshaded areas are visible.